If you look around, I mean, everything is trending electric. You've got this massive shift to EVs, smart grids, smart homes, and every single bit of that relies on clean power. And right now, that means solar.
Exactly. Solar is absolutely essential, but there's always been this trade-off. You have crystalline silicon, which is, reliable, but it's expensive, it's bulky. And then for what feels like the last decade, we've had this promise of perovskite photovoltaics or PVs that were supposed to be cheaper, way more efficient, and just easy to manufacture.
The energy miracle we were all waiting for, but there was this huge paradox, right? I mean, what if I told you that the process to make these amazing, cheap solar cells, it relied on chemicals so toxic they made the whole thing impossible to scale? It was this green tech with a really, really dirty secret.
And that's the core of the problem. That's what held perovskites back for so long. For years, they were just this theoretical gold standard.
Right.
But turning that promise into an actual product, something you could see on factory floors, it just kept hitting these three non-negotiable barriers. And if you failed one, you failed them all.
Barrier number one, the use of these incredibly toxic solvents, a huge environmental and health hazard. Barrier two, a total lack of uniformity when you tried to make them big enough for commercial use. And barrier three, which really matters to anyone living through a hot summer or a rainy winter, they were too fragile to survive in the real world.
So today, we're diving deep into the source material that finally cracked that code. Our mission is to unpack these new findings that show an environmentally responsible and, critically, a highly reliable path for perovskite panels to finally hit commercial scale, to compete head-to-head with silicon.
And we are pulling this straight from the source. The groundbreaking research article, Improved Solvent Systems for Commercially Viable Perovskite Photovoltaic Modules, published in the journal Science. This was a massive effort, a huge team. We're talking Yinke Wang, Heron Tan, Kishao, and others from places like Nanjing University and the manufacturer Shine Solar.
Huge.
This is real lab-to-factory science.
Okay, let's unpack that first big hurdle. How do you make a perfect product without, using poison? It's where it all begins. To make a perfect crystal, which is what the perovskite layer is, you have to deposit this precursor ink. And historically, to get the right quality, researchers leaned on these really hazardous solvents. I mean, we're talking about compounds like 2-methoxyethanol or 2-me and N-methylformamide, DMF.
Right, DMF. And for anyone listening, why were those such a deal breaker? It sounds like pretty standard industrial chemistry.
Well, they are standard, but they're completely incompatible with modern manufacturing, especially in ambient air. These chemicals they're highly volatile and they have significant biotoxicity. If you tried to scale this up to a gigafactory, I mean, you'd have regulatory nightmares, worker safety concerns, you'd need massive air filtration. It's just not viable. You can't have a green product if the creation process itself is hazardous. And the industry needed a true green ink.
So this is where the team got creative. They couldn't just find a less toxic chemical, right? It had to be less toxic and still make a perfect film. So what was the solution?
They engineered a totally new 3-part green solvent system. It's based on 2 knowns, GVL and DMSO, but the genius move, the real breakthrough, was tuning that mixture with a 3rd solvent, 2-methyl tetrahydrofuran or 2-methyl-F.
2-methyl. That's the sustainability game changer here, isn't it?
Absolutely. This is a massive win for the planet. Unlike those other chemicals, the DMF that's derived from petroleum, 2-methyl comes from renewable biomass. It's got lower ecotoxicity, it's more biodegradable. So they weren't just swapping chemicals, they were swapping a fossil fuel derivative for a sustainable plant-based one.
Okay, that sounds great environmentally. But that does bring up a real question about scalability. If this new ingredient comes from biomass, is there actually enough of it to start coating solar panels at the gigawatt level, for the US and the global market? Does the green process create a new bottleneck?
That's a critical question for commercialization. And, the source material doesn't dive deep into the supply chain logistics. But the choice of 2-methyl itself suggests they're thinking ahead. Biomass-derived chemicals are a huge focus globally, and that process is just. It's so much more sustainable than relying on limited, hazardous petroleum. The shift itself points to viability.
Fantastic. So they've gone green. Now, how does this new chemical cocktail make the actual solar film better? It has to outperform, not just be safer.
Right, and this is where the chemistry is just. It's really elegant. The analogy of baking a cake is perfect here. When you lay down this wet precursor ink, it has to crystallize into a perfect perovskite layer. But the old methods, even with less hazardous solvents, they evaporate too slowly and unevenly.
And when the batter dries too slowly, you get flaws.
You get huge structural flaws. The biggest problem is what they call voids. We're talking literal air bubbles and defects right where the perovskite meets the substrate. If you look at an old film under a microscope, it's just riddled with these tiny cracks.
Mm.
And those defects, they kill efficiency and let in moisture, which destroys the panel over time.
Ah, so 2-mouth-F is the magic ingredient that fixes the baking process.
It's the perfect regulator. It has two critical properties: high vapor pressure and a weak coordination ability. Just think of it as a rapid, controllable drying agent. It speeds up the evaporation of the other solvents in a really controlled way. And that fast, uniform evaporation, it promotes immediate, high-quality crystallization, specifically of the stable alpha phase you want.
So instead of a slow, uneven dry that leaves all these gaps, you get an instant, perfect setting of the material.
Exactly. The researchers confirmed it. They created void-free, high-crystalline, defect-minimized perovskite films. They solved the toxicity problem and the core material quality problem at the same time, at least on a small scale.
Which brings us right to that second barrier, scale. You can make a perfect little chip in the lab, but the second you try to print a massive sheet, say 120 by 60 centimeters, commercial size, the whole process just falls apart, especially at the edges.
Scaling up is where so many breakthroughs just die. The technique they use is called slot die coating. For a mental image, just picture a giant squeegee applying that ink in one smooth, continuous layer across a huge surface at high speed. It's what you need for mass production.
But I can already see the problem. If I spill water on a counter, the edges always dry first.
Precisely. The edges and corners are the Achilles heel. Solvent evaporation is always fastest there, and that causes premature crystallization. It's defective.
Right.
And that ruins the uniformity of the whole module, which just tanks your total power output.
So how on earth do you keep the edges from drying out too fast?
They developed this brilliant but chemically simple technique. They call it the Solvent Confinement Edge Protection Strategy, or SCKP. The key is just a tiny addition to the ink, a surfactant molecule called TAC.
Surfactant. So we can think of that like soap, right? Something that lowers surface tension.
You got it. Soap lets water spread more evenly. TAC does something similar for the ink. It's added to the mix, and it self-assembles at the liquid surface of the wet film.
And what does that do on a massive scale?
It manages the solvent dynamics right at the edge of the panel. Normally, that fast evaporation at the edge causes this thing called the Marangoni effect, which is a fancy term for solution flowing because of surface tension differences. The liquid rushes to the edges. TAC suppresses that. It slows down the evaporation right at the boundary, right where the failures usually begin.
So the tack acts like a speed bump, but just for the edges. It makes sure the entire sheet crystallizes at the same rate.
That is the entire goal. It ensures consistency from the center all the way to the perimeter. And the evidence for this is just overwhelming. They measured the quality using something called photoluminescence decay lifetimes.
Okay, let's translate that for everyone listening.
Absolutely. Basically, it's a measure of how clean the material's internal structure is, how long the energy it absorbs stays trapped and useful before it just leaks out because of defects. So a longer lifetime means a cleaner, better film.
And what did the SCEP films show?
A dramatic improvement. The SCEP films had these significantly longer lifetimes at the edge. We're talking 247 nanoseconds. Compare that to the control films, which only got 130 nanoseconds. So they nearly doubled the material quality right where it's usually the worst. And that translated directly to uniformity. Across a big 30 by 40 centimeter area, the thickness variation was only 6.5%. That kind of consistency is just non-negotiable for commercial success.
Okay, that handles toxicity and scale. So now we hit the third barrier, and maybe the toughest one for perovskites: reliability. All this incredible chemistry means nothing unless it can survive a hurricane, humidity, blistering heat. Can these things actually last on your roof for decades?
This is the part that moves perovskites from the lab to the investment sheet. All these innovations led to the production of genuinely large-scale modules, 7,200 square centimeters.
That is massive. Most early perovskite work was on cells maybe a square centimeter. This is a real-world module size.
And here is the wow factor.
Yeah.
The independent verification. They didn't just claim it was efficient. The National Renewable Energy Laboratory, NREL, certified that this large-scale module achieved a total area steady-state efficiency of 17.2%.
Why is 17.2% so significant for a module that big?
Well, commercial silicon panels today, they might hit 18 to 20%. But historically, large area perovskites struggled to even reach double digits because of those uniformity problems. Hitting 17.2% on a huge 7,200 square centimeter module proves that this new green manufacturing process works. It's factory ready, and it's immediately competitive.
An NREL certification is the gold standard for efficiency, but what about the durability? The real test, what did they have to pass to be considered ready for deployment?
They had to pass the most demanding standard in the solar industry, IEC 61295. Think of it as the ultimate stress test. It's certified by the Technical Inspection Association, TÜV Rheinland, and it simulates decades of real-world abuse. Extreme heat, temperature cycling, humidity, continuous operation, the works.
And did they pass?
They pass all of the IEC 61215 standards, and the results are genuinely startling, especially in the damp heat test. This is the killer for perovskites. It simulates humid tropical conditions, 1,000 hours at 85 degrees Celsius and 85% relative humidity.
Okay, so how did their SCEP module do compared to a traditional one?
This is where you see the void-free film strategy pay off. The SCEP module maintained 100% of its initial efficiency after the full 1,000 hours. The control modules, for comparison, they degraded badly. They plummeted down to 73.4% efficiency, 100% retention after that kind of abuse.
Yeah.
Well, it's unheard of for this tech. It directly validates the quality of the crystallization.
Wait, 100%? That's almost impossible for a new technology. What's the change in the material science that stops that moisture from getting in?
It all comes back to those microscopic voids, because the SCEP process, which is enabled by the green 2 MECF, creates such a dense, void-free film. There are just no pathways for moisture to penetrate the active layer. The film's own density and uniformity provide this built-in, robust defense against the environment.
And what about just running them day after day, continuous operation?
That's the operational stability test. They ran them under continuous maximum power point tracking, which simulates the module constantly optimizing its output under the sun. After 1050 hours, they still had 97.2% of their initial efficiency. Again, the control group lost nearly 20% in the same test. So it proved the panels are stable while they're actually generating power.
And if we look at the relevance for you, the consumer, someone living in a hot climate, say Phoenix or Texas, there's one metric that gives this panel a huge commercial advantage over silicon: the temperature coefficient.
This is the game changer for grid stability in hot places. Every solar panel loses some efficiency as it gets hotter. The hotter it is, the more power you lose. This Perovskite module measured a temperature coefficient of only minus 0.11% per degree Celsius.
Okay, let's put that in context. How does that compare to what's out there now?
Standard crystalline silicon modules, the ones on rooftops everywhere, they typically range from minus 0.29% to minus 0.39% per degree Celsius.
So the new green perovskite modules lose nearly 2/3 less power than standard silicon panels when it gets really hot. That is a massive advantage.
It's a phenomenal selling point, and the researchers confirmed this outdoors. When temperatures got above 30 degrees Celsius, the perovskite panel was just. It was more stable in its power generation than a standard silicon panel. This means that during the hottest part of a summer day, when you need that electricity for air conditioning, these new perovskites perform better. They're not just stable, they're actually better suited for hot climates.
This is truly a breakthrough. It addresses the entire life cycle, from green chemicals to real-world performance. So let's wrap up our deep dive with the core takeaways.
Takeaway 1. This research provides a truly environmentally responsible and scalable path for solar manufacturing. They got rid of toxic, petroleum-based solvents and replaced them with sustainable, renewable biomass derivatives, like 2-MECF. That just eliminates the major health and safety barrier.
Takeaway 2, the SCP strategy. That innovation finally enabled high-quality, large-area manufacturing, and that's what let them hit that NREL certified efficiency of 17.2% on a huge module. It proves they're factory ready.
And takeaway 3, independent third-party validation from NREL and TÜV Rheinland. It confirms these green scalable modules meet and exceed the toughest international standards. 100% power retention in that brutal damn heat test and superior performance in high temperatures.
So the big picture here is that perovskite PVs have now shown they can overcome every single critical bottleneck: the toxicity, the scale, the stability, everything that kept them from competing with silicon. This isn't just a lab curiosity anymore, it's a commercial blueprint.
Exactly. They've moved the science so far forward that now, really, the only barriers left are manufacturing ramp-up and market adoption.
So given that these new modules are stable and they perform better than silicon in the intense summer heat, the question for you to think about is, how quickly might these green perovskite solar panels start dominating the U.S. solar market, from huge solar farms to your neighbor's rooftop?
An important question to consider for sure as this tech moves out of the lab and into the sunlight.
Thank you for joining us for this deep dive into the future of clean energy manufacturing. Be sure to subscribe to the channel for more explorations into cutting-edge science.